Yes, sadly, that's the passage of time. Well, welcome, everybody. Destroyer of Worlds, well, as you can see, it's a book that I've just brought out, but the background to it is sort of unusual. So I thought I'd just start with telling you how this story came about and then take you through the story. Well, it began about 4 to 5 years ago. I was walking into town with my grandson, who was then 10 years old, and he suddenly said, "Grandpa, what do you know about Tsar Bomba?" And I said, "Well, tell me." And he started saying, "Well, you know, this is a 10-year-old kid. Oh, it was the biggest bomb ever exploded. The Russians did it in 1961 over Novaya Zemlya, blah, blah, blah." I thought, what on earth are they teaching them in school nowadays? But I went away and I started researching it, and I quickly became fascinated because the whole story had really started back in 1896 with Henry Becquerel in France discovering a little smudge, the thing that you see at the bottom of this picture, on a photographic plate that he had put next to some uranium. And at that stage, that was the first hint of what we now know, the energy leaking spontaneously out of the nucleus. But it was almost missed. It was just such a little thing. How does it come about that with that single clue to something, within 70 years, you've designed something that could literally destroy everything? So that I became fascinated by. The second thing was that in 2023, unanticipated, I suddenly got hit by cancer, thankfully dealt with successfully, but it meant that for 6 months I couldn't do anything other than go for chemotherapy every 3 weeks with a bit of radiotherapy, using some of the good things that nuclear physics has done for us, I should say. And that was when the Oppenheimer movie was all the rage. And so I thought of having the idea of writing the prequel to Oppenheimer and the sequel to Oppenheimer. And then eventually I managed to see the movie, and my 2-line summary gave me the thought of what I would do for this talk. I'll have a series of hits or myths of things that I uncovered while researching the story of this whole history. And the 2-line summary of the movie, if you knew nothing other than the movie, then the impression you would probably have is that the film was about the father of the atomic bomb, and that the only thing that the British contributed to the whole Manhattan Project was the spy Klaus Fuchs. Challenge, is that a hit or is it a myth? Well, we'll come back to that later on. So the first thing to do, we've got to solve this clue that Becquerel has found. And in any good crime scene, you go back. I mean, how did that come to be anyway? And as we're at the RI, I thought, well, let's go right back, because I see the development of nuclear energy as the third industrial revolution. The first industrial revolution was back in the 18th century, which was mechanics. It was water turning into steam and driving engines. Water is H2O. Steam is H2O. So nothing changes at the atomic level, but their configuration changes. So that was the first industrial revolution. What it was that made atoms do their thing and work was the theme of the second industrial revolution, which actually, it's ironic, this is the only time in my life that I have got shown a picture in a lecture of somebody standing at, well, not exactly this, but what its precursor was, here in the Royal Institution. Michael Faraday, the discovery of electromagnetism, which was the driver of the second industrial revolution. Actually, as I look around the audience here tonight, and the lecturer for that matter, I don't think we're quite as well dressed as they were in those days, though it probably wasn't as hot in those days either. So anyway, so that was the second industrial revolution, the discovery of electricity and magnetism and all that it can do, which then raised a very intriguing question: what actually is electricity? And when I was a student at high school, I bought in a jumble sale a book for 1 penny, that was 1D, the old currency, called Key Questions in Science. It was a Victorian book, and in it, the fourth question was, what is electricity? And the answer given was, it is an imponderable property of matter, the like of which is not understood. So that was what was actually going on at the end of the 19th century, was to try to understand the nature of electricity and electrical phenomenon. And from that, by a sort of series of accidents, we come to Henry Becquerel discovering radioactivity. The key thing perhaps was the end of 1895, the discovery of X-rays by Röntgen in Germany, and nobody knew what they were. That's why they were called X, for the unknown, in a sense. Henry Becquerel was very interested in fluorescence. That's the property that some minerals have, that when you expose them to light, the energy from the light gets stored up, and then the mineral will glow in the dark later. And Becquerel wondered if X-rays were somehow related to fluorescence, so he decided to do some experiments with uranium salts that he knew fluoresced. But first of all, he had to energize them. And fortunately for history and for him, though unfortunately for him at the time, it was January in Paris. It was very, very dark. He was working in a little room at the top of a 3 or 4 story house, and he never got any decent sunlight to irradiate his samples with. So after 3 weeks, he decided to develop the thing anyway, even though he hadn't energized them. And to his shock, he discovered this little smudge that you see there, which showed that uranium is spontaneously radiating energy, even in the dark. And that was the moment that the beginnings of what will eventually become the atomic age were born. So if you're thinking of this like a CSI program, you know, this is the clue to something. What is it? And the first question we might ask here is, okay, so what do you do next? Well, the things that were done next were really these people here, the famous Curies, Marie and Pierre Curie on the left, and then the New Zealander Ernest Rutherford, who came over, eventually settled in Cambridge over here. Ernest Rutherford discovered that there were 2 forms of radioactivity. He called them alpha and beta. About that, we don't need to say anything very much right here and now. It was the Curies who made the first breakthrough, where they were able to measure very precisely not just the fact that energy was being emitted and fogging photographic plates, but to measure how much energy was being emitted, how intense it was. And they discovered that rock samples that contained uranium were radioactive, as you would expect, but the amount of radioactivity coming from the rocks was more than could be explained by the uranium alone. And it was through this that they refined their samples and discovered 2 new radioactive elements. Polonium, which was named after Marie Curie's origins, Poland, and radium, which is so radioactive that it actually glows in the dark. And Rutherford, in his experiments, discovered radon, the radioactive gas. Now, I've shown them here in a series that they didn't know this. We know today that uranium, which is number 92 in the periodic table, decays by alpha radioactivity, jumping 2 places at a time down the table to thorium, then to radium, then to radon, then to polonium, and eventually settling up as lead. I've just shown it here so we've got something to hold on to, but at the moment, they're almost literally in the dark. There are 3 radioactive elements, one of which, radium, as I said, is so powerful it glows in the dark. Now, Rutherford was measuring the amounts of energy produced in uranium decays, and he met the Curies in Paris in 1903. And afterwards, after having dinner together, they went up to the roof of the apartment, and you can imagine Paris in 1903. It was August, it was a very clear night. There weren't any street lights in those days, so it must have been quite a vision. They could see the Milky Way across the sky. And Pierre Curie then dramatically produces from his waistcoat pocket a little glass phial with radium in it, glowing. And Rutherford's wife recorded in the diary that it was glowing brighter than the Milky Way. The other thing that they noticed was there was enough illumination coming from that radium sample that they could see that Pierre's fingers were already getting damaged. That was the first hint that radioactivity can cause damage. But that was the first moment when they realized that radium is putting out a vast amount of energy. And Rutherford calculated that radium must somehow contain vast sources of energy, and this gave rise to a thing that you often see stated, that if you had an apple made of radium, about a kilogram of radium, that there's enough energy there that it could drive an ocean liner from Southampton to New York. So the first quiz question for you all tonight is, how many people believe that that statement is correct? How many people believe that statement is false? Okay, many people didn't vote, which is probably wise, because all those of you who thought it was correct are wrong, and all those of you who thought it was wrong are also wrong. The actual answer is, yes, it could, if you're prepared to spend a century over the trip. And this was the sort of enigmatic situation they were in. You have discovered this remarkable source of energy. But when you think about it for a second, the fact that it has been in these elements for as long as they've existed, 4,500 million years, then it must be coming out extremely slowly. And that, if you like, is the problem. You've got this wonderful source of energy, except it dribbles out so slowly, you can't do very much with it. So how are you going to be able to speed it up, to make it come out fast enough that you can get useful power out of it? And so the first thing is to understand what is going on. And that, like in any good detective story, is where the author introduces another clue. And this is indeed what happened, because as we started here, we had Michael Faraday. It was trying to understand the origins of native electricity, was the discovery of the electron in 1897 by J.J. Thomson in Cambridge. The electron, we now know, is an electrically charged particle that exists in the outer regions of atoms. And they carry negative electric charge. Each electron carries a trifling amount of electric charge, but as they move through wires, their flow is what we call electric current. And it's interesting that if you each now just take a deep breath for a second and hold it for a couple of seconds. Now breathe out, thank you. You just breathed in a million atoms of oxygen and nitrogen, and in each of those atoms, there are 7 or 8 electrons. And if you add up the total amount of negative electric charge that you just breathe in, that is enough to ignite 100 thunderstorms, lightning bolts. Thank you, that's the right reaction. So the reason why we are all able to do this is the fact that, of course, in addition to the negatively charged electrons, there is positive charge somewhere in the atom. So that is the immediate inference that they were immediately aware of way back at the start of the 20th century. There must be positive charge somewhere, and that was finally sorted out by Ernest Rutherford and there's Hans Geiger, one of his assistants. They discovered that the positive charge of the atom is concentrated on a very compact nucleus in the middle. And Niels Bohr, shown on the right, who was a great Danish theorist who was also visiting Rutherford in Manchester, built the little model of the atom that it's like a miniature solar system. I mean, it's not really, but it's a very useful picture to keep in your head. The idea that the electrons whirling around the outside are like the planetary electrons, and the nucleus is the compact sun at the heart of the whole thing. So that was the picture that had emerged in 1911, a very massive, dense, positively charged center with the negative electrons whirling around the outside. And also Rutherford managed to demonstrate that this energy that was coming out from these atoms in radioactivity was originating in the nucleus. How? Didn't know. What the nucleus is, didn't know. All they knew was the nucleus was positively charged and very massive. That was where they were come 1911. We now know that, well, Rutherford showed that the positive charges, that all nuclei contain what's called protons. That protons are the positively charged particles that the more of them you put together, the bigger the total you have. So hydrogen, the simplest atom, has got 1 proton with 1 electron whirling around. Helium, the next one, has got 2, all the way up to uranium with 92. So it's the protons that carry the positive charge in the atomic nucleus. But that wasn't enough to explain the relative masses of these atoms, because helium has got roughly 4 times the mass of hydrogen, even though there are only 2 protons. So that gave the insight that there must be 2 more neutral things like protons to make the mass. And those are called neutrons. And they were discovered finally in 1932 by James Chadwick. And I just show this little thing down the bottom because this was one of the things that I stumbled across, that there has been a lot of confusion about precisely when Chadwick made this discovery. In the classical Bible, The Making of the Atomic Bomb by Richard Rhodes, has some footnotes about this, which sadly gets it all wrong. I've found that there was indeed, the announcement was made at a meeting of what was called the Kapitza Club at Trinity College in Cambridge, and the only records of it are the date, the title of the talks, and the signature of the speaker afterwards. And there it is, 23rd of February 1932, James Chadwick announced the discovery of the neutron. What was intriguing was to see neutron with a question mark. You know, just showing how, in that first moment, there's still uncertainty, there's still work to be done. But that is what we have. 1932, as of the 23rd of February, it's established that nuclei are made of protons and neutrons. And so now you have got the beginnings of a picture of what might be going on, and it was really Niels Bohr, the genius Dane, that came up with this first insight. So let's sort of picture it. It's quite easy to picture the things, imagining protons as the red objects and neutrons the black objects. They're identical pretty much in all respects, except these are charged and these are neutral. So the more of these you have, the further up the periodic table you are. You can put as many neutrons as you like with these to make what's called isotopes, but that is getting beyond what we need to be with at the moment. So picture in your mind this lump of protons and neutrons. All those protons are positively charged. And one of the first things we learn about electricity at school is that like charges repel. So there's a huge amount of electrical repulsion trying to blast those protons apart. Yet they stay compactly in this bundle. And that is where the neutrons come to work, because in the atomic nucleus, there is a very strong attractive force between neutrons and protons, strong enough that it will hold the whole bundle together, even though the electrical force is trying to blow it apart. Where that strong force comes from, we don't know, well, we do today, but we don't need to know, other than it is there, and it must be that force that is providing this energy that is somehow leaking out in radioactivity. So these were the sort of pictures they had. But if you can sort of picture this for a moment, realize this is a pretty tense situation. You've got electrical repulsion and this strong force competing with it, and they're sort of balancing out. It's sort of highly unstable. And you get a lump which is probably unstable, and nature likes stability. So if it is unstable, got high energy, it will become more stable by getting rid of the unwanted energy. And it's getting rid of that unwanted energy that is the energy that materializes itself in radioactivity. And the particular way that it does it, alpha emission, is that two protons and two neutrons clumped together form what in the jargon we call an alpha particle. And if you've got an unstable nucleus with lots of protons and neutrons in it, if the two and two pop off, it becomes more stable. So alpha radioactivity is an unstable big nucleus, a bit spontaneously pops off, and it becomes more stable. And this is the good old E equals mc squared at work. The mass of the nucleus multiplied by the velocity of light squared is the amount of energy that's in there, minimize the energy to stabilize it, and the spare energy comes off in these alpha particles. So that was what was going on, but they didn't know how it was or why it was, but indeed empirically, that was really the story. So who are the people that you may not have heard of that were involved in this sort of thing? Lise Meitner and Otto Hahn are the two names. Lise Meitner was an Austrian Jew, and Hahn was working at the University of Berlin. They started working together in 1907, and in the 30 years of their collaboration, they are the people who really established what I call the radioactive ladder. The fact that every time you emit an alpha particle, because the alpha particle contains two protons, That means what you end up with has got 2 fewer protons than you started with, which means that you have moved 2 places down the periodic table. So uranium to thorium, 2 places, thorium to radium, 2 places, and so on down to lead, an alpha particle each time. Beta radioactivity, Meitner in particular was able to show, involves a shift of 1 place, and that takes you from even numbers to odd numbers. So you're starting off with uranium at 92, and you can get into the odd number sequence. I've put protactinium number 91 in blue because Meitner and Hahn discovered that element in 1917, and then the alpha decays from that take you down to bismuth at 83. So the ladder of radioactivity, the taxonomy of it, if you like, was established by these people. I've just introduced them because they will play big roles later on in perhaps somewhat controversial circumstances, but let's come to that in due course. Time for the next Trivial Pursuits question. So this photograph shows, in my opinion, the greatest female physicist of the first half of the 20th century. To give you a clue, that's the Curies. The one on the left is the answer, hit or myth. Well, the answer, in my opinion, is the little girl, because the little girl is their daughter Irene, and by 1930, she is a physicist in her own right, with her husband Frederick Joliot, the Joliot Curies, as they are known. And in 1934, they made the discovery which has been described as second in importance in the history of atomic and nuclear physics to the discovery of the nucleus itself. They found the first breakthrough in how to change the natural chronometer of nature. Remember how we started? I said radium is leaking out energy, but they're all leaking out energy so slowly, it's not fast enough to do anything very much with. They discovered how to speed things up. They used these alpha particles that were being produced in natural radioactivity and irradiated atoms of aluminium, ordinary sort of stuff, with the alpha particles. Now, aluminium, I can't remember, is it number 27 in the periodic table? It's got, well, maybe it's not that much, but anyway, it's got quite a bit of positive charge on the nucleus, but not a lot. So the alpha particle, which is positively charged, can penetrate and get through this electrical shield that's trying to deflect it. When you've got a very big nucleus like lead and uranium, the positive charge on the nucleus is so big that alpha particles can't get in, they just get deflected. That's how Rutherford discovered the existence of the nucleus when he had gold atoms here. A big electrical shield was deflecting the alpha particles violently, and that was what led him to deduce that there must be this positive center. But if you come down the periodic table to the lighter elements, then the shield, because there's fewer protons in there, the shield is not so strong, and the alpha particles can penetrate and get in and disturb what is already there. And that is what the Joliot-Curies discovered, that they could irradiate ordinary material that had been stable for 4.5 billion years and induce radioactivity in it. Now, that was a very interesting discovery, but it had immediate applications. And one of the applications is that it is the key to much of modern medicine, radiology, PET scans, and so forth, that you take ordinary matter, induce radioactivity in it, and then the radiation that is emitted can be used as a diagnostic or a tool. And this is something particularly interesting to me because during the course of my 6 months, I had 4 PET scans, and for me, the Joliot-Curies, the destroyer of worlds for me is the destroyer of the cancer cells that radiation was being put to use. And I find it somewhat ironic that when you talk about nuclear physics to the public at large, the immediate picture that they have is of terrible things like bombs and so forth. It's a bit ironic that I'm writing a book that ends up with the punchline about destroyer of worlds and all the horrible things that have come from that original discovery, while at the same time I was benefiting from the good things. And actually, as I will argue later on, I think had the Second World War not happened, it's very likely that the atomic bomb itself might have been at the very least significantly delayed, but we will come to that. And the image of nuclear physics would have been a very positive one. The amount of things that can be done by inducing radioactivity in ordinary material and then putting it to use is legion. So I think it is the Joliot-Curies that are perhaps the first heroes in this story, and it's for that reason that I regard Irene as the greater of the Curies. One of the things, again, that I discovered while researching this was that I, like many of you, I guess, had grown up with this picture of Marie Curie as being one of the greatest scientists of our time associated with radioactivity, which is indeed true, but they discovered the radioactivity back at the start of the 20th century, and she didn't actually do anything with it. They spent all the time making better and better sources of alpha particles, but they didn't put it to use. It was Irene and her husband who finally put it to use and started making scientific discoveries as a result. The other approach to getting energy out of the atom was to do it by brute force. And that was what began in 1932. 1932 was a remarkable year. It was the year when the neutron was discovered. It was also the year when the first atom smasher, as it became known, was built. And that was at Cambridge, the Cavendish Lab in Cambridge. The idea was, Rutherford was very much aware, as I said, it's very hard to get into the nuclei of heavy elements because the electrical shield against naturally produced alpha particles is too powerful. Rutherford said there's two ways that we could get in. One is to have much better sources of alpha particles. Well, that's what the Joliot-Curies had. But Rutherford didn't have access to those. Or to speed the things up, so they've got more energy to get in there. And that is what he did with Cockcroft and Walton, the two assistants. They didn't use alpha particles, they used protons. Hydrogen atoms are the simplest of all. If you use an electrical force to strip the electron, you're left with the proton. The proton is positively charged. If you can then use another electrical kick to make that proton move off, well, accelerate it, it will emerge through an electrical field and blast into a target of lithium, for example, and get in, and we see what happens. And that is basically the idea behind the first atom smasher that Cockcroft and Walton built. In passing, I'll just make the comment that we're seeing the nature of science also evolving here, that up to this point, we have been talking about one person or maybe two people working together, doing experiments on a bench top like this, with the bits and pieces that come to hand. They probably might get a glass blower to blow glass tubes if they need some extra stuff to pass gases through and so forth. But that was the limit of it. It was a very small scale, bits and pieces, strings and sealing wax, as it became known. 1932, the atom smasher is, we now say, the beginning of big science, that instead of having a benchtop experiment in an office, you've got something that would require the size of the theatre here to have the electrical field speeding the protons down to hit the target down the bottom. So it's the beginning, we would now say, of big science. The discovery that they made was that when a proton hit lithium, it split it in two. Now, this is the easy part of nuclear physics, just being able to count that the black solids represent protons and the open circles represent neutrons. So lithium, which is the third element in the periodic table, hydrogen, helium, lithium, it's the lightest metal that there is, has got 3 protons. That's the 3 black circles. Lithium-7 means that there are 7 in all. That's 3 protons and 4 neutrons. So if a proton hits lithium-7, what happens is it splits it into 2 protons and 2 neutrons, the nucleus of helium-4, what we call the alpha particle. So it split it into 2 alpha particles. That's what Cockcroft and Walton discovered. In fact, you could say this was the first observation of fission, a nucleus having been split literally into two. But they also measured the amount of energy that was released in this process, and it fitted precisely with what Einstein's equation E equals mc squared would say it should have happened. And so that was also the first experimental confirmation that this famous equation actually applies in the real world of nuclear physics. So that, for a moment, would appear to be the philosopher's stone and perpetual motion, whatever the word I'm looking for is, that the amount of energy that is released in that process is greater than the amount of energy that is taken to speed that proton up and smash it in the first place. So at first sight, you think, at last we've found a way of getting not just energy out of the nucleus, but getting more energy out than it costs us to do it. This is the point where Rutherford made his famous remark, anyone who claims you can get useful energy out of the nucleus is talking moonshine. The problem is, everything I've told you is true if I had one proton and I could guarantee to use energy to speed it up and smash it into a lithium and split that into two, I would get more energy out than it costs me. The trouble is that the chances are the proton misses it or tickles it, doesn't do that. You have to do it maybe 1 million times for one of these things to actually do it. So it's so hugely inefficient. In practice, it's costing you much more energy to speed a beam of protons up to get the occasional one to do the job. And it was in that sense that Rutherford said people were talking moonshine. If indeed he actually said that, because when you start writing books and you've got editors who want you to check everything, you say, well, what's the evidence he did say that? And you go back and check it. He apparently said it at a meeting of the British Association in Leicester in 1933. Well, the British Association, it's possible to go to the National Archives and find the proceedings of those meetings. And Rutherford indeed had a big session all about nuclear physics and so forth, but nowhere in there does he make any statement at all like this. But the statement appeared in the Times newspaper the following day. Now, those of you who have been to a BA meeting know what happens. You know, there's a lot of media people that come along, and then afterwards they ask questions, and then they write their reports up. And obviously what had happened is that after the talk, somebody, the Times correspondent, had asked Rutherford the question, is it possible to get energy out of the nucleus, blah, blah, blah. And it seems that Rutherford had made this remark, he's talking moonshine, unless we find some other way. I mean, you know what the media are like. They don't like caveats, they like headlines. And so that caveat never appears. But that is what he was reported to have said. And that is what appeared in the newspaper the following morning. And one result of that was that it did indeed inspire this man, Leo Szilard, to have the idea, which a few years later would indeed turn out to be key to pretty well everything that happened, namely the idea of what's called the chain reaction. Now, the story of this, I will just read you briefly before telling you what this is all about. Richard Rhodes starts his whole, how many pages? 800 pages, with the story of Leo Szilard. In London, where Southampton Row passes Russell Square, across from the British Museum in Bloomsbury, Leo Szilard waited irritably one grey depression morning for the stoplight to change. It was Tuesday, September the 12th, 1933. The stoplight changed to green. Szilard stepped off the curb, and as he crossed the street, time cracked open before him as he had this marvellous insight. And it was this. Suppose instead of starting with the proton that Rutherford had done, you had started with a neutron. And instead of using lithium-7, you moved one further step up the periodic table to beryllium, beryllium-9. So now you've got 4 black balls and 5 white balls being hit by a white ball. And when you take 2 alpha particles off, you're left with 2 neutrons. And so this is the brilliant insight, as he said late at the very end of Rhodes' chapter, as the light changed to green and I crossed the street, there we are, Southampton Road, in 1933. As the light changed to green and I crossed the street, Szilard recalled, it suddenly occurred to me that if we could find an element which is split by neutrons and which would emit 2 neutrons when it absorbs 1 neutron, such an element, if assembled in sufficiently large mass, could sustain a nuclear chain reaction. And then, dramatically, Leo Szilard stepped up onto the sidewalk. Behind him, the light changed to red, and the world changed. Hit or myth? How many people think it's a hit? Oh, well, I should be clear. I'm not asking, do you believe that Szilard had the idea? Szilard definitely had the idea, and he definitely had it to beryllium. I must say, the only thing that I had always been worried about was how did the traffic signals give him the idea of neutrons? But I think the idea of neutrons, that at least I understood from the way I presented it. But what I'm really saying is, do you believe that he had that idea as described here so eloquently by himself, and it's become one of the factoids of the history of nuclear physics? So how many believe that he discovered it while walking across the crosswalk at Southampton Row in 1933 as the traffic lights changed? Quite a few say yes. Any say no? Righty-ho, okay. Those who say no, are you just guessing or have you got a reason? Good question. To the best research I've been able to do, it seems the first traffic lights in London were at Piccadilly Circus in 1937. Now, what I suspect is the following. We know that Szilard, another of the Jewish emigres, moved across to the States and spent the rest of his life in North America, where, of course, crosswalks with flashing red and green people are commonplace. And I think that later in life, he probably fabricated or confabulated all these things together, and this story gained a life of its own. It's a great after-dinner story, but its factual basis is probably zero. Anyway, so let's move on to the next bit of this. So he has had the idea of nuclear fission. We now know that it doesn't work with the very light elements. That beryllium example that I showed you, indeed, it's correct. 2 neutrons would come off. But when you do the E equals mc squared, that's the hard bit of it, it turns out it actually costs you more energy to do that. The reaction would like to go the other direction, not this way. If you go up to the other end of the periodic table to uranium, then it does turn out that this will work and you do liberate energy. And that is the nuclear fission that is going to be the dramatic part of the story in a few minutes. But this part of the story is another thing where I've got a hit or a myth. Nuclear fission was discovered by Hahn, that's the same Hahn as Meitner and Hahn, by Hahn and Strassmann, hit or myth. So I heard somebody shout myth. Any other wants to heckle and shout hit? I mean, it's in all the books, so it must be true. Right, okay, well, let's see. First of all, the picture on the left, this is a slight red herring, it's not the part of this story, but that's Enrico Fermi receiving the Nobel Prize in December 1938 for having discovered transuranic elements, apparently. He had been doing similar to what the Joliot-Curies did, but instead of using alpha particles to invade nuclei, he used neutrons. The point being that the Joliot-Curies could get alpha particles inside the electrical shields of the light elements, but they couldn't they couldn't beat the shield of the very heavy elements because the alpha particles get repelled. Fermi used neutrons, which don't feel any electrical forces, so they can get in. And he induced radioactivity in 60 elements, and by the time he got to uranium, he then started finding some very strange results that he couldn't interpret. They didn't fit anything at all that made any sense. And so he assumed that what he must have done was made what we now call transuranic elements. You know, Uranus, Neptune, Pluto, uranium, neptunium, plutonium. That uranium is the heaviest naturally occurring element on Earth today. But you could imagine many more protons and neutrons making heavier and heavier things, elements beyond uranium. Now, 4.5 billion years ago when the Earth formed, these things were probably there, but they're so unstable they'd all decayed away. But if you could attach a neutron to uranium, and it then goes through a beta decays and so on, you might be able to move up to neptunium and plutonium. And that is what Fermi thought that he had done, and that's what he won the Nobel Prize for. It's quite possible that actually his strange signals, because he had discovered what we now call fission, that the uranium had split in two. He did that experiment in 1934. It is fascinating to conjecture how history might have been different had the results of Fermi's experiment in 1934 in Italy, which was under Mussolini at the time, had been understood and recognized for what they were. And if you move the whole of the fission to explosive energy to atomic weapons forward by 4 to 5 years, you've got a completely different version of history. But that's for some political fiction writer to write. In any event, that's just a passing comment for this. It is not the answer to my question, did Hahn and Strassmann discover it? It is ironic that just a couple of weeks after Fermi's Nobel Prize, that Hahn and Strassmann reported on the experiment which is taken to be the discovery of nuclear fission by them. So let me just say what it is that they had done. We now know that what they had done was, and what Fermi had probably done, was that the neutron hits a lump of uranium, number 92 in the periodic table, there's 92 protons in there and lots of neutrons, and split it roughly in two. They discovered, because they were very good chemists, they were able to show that the products of this included barium. Barium is number 56 in the periodic table. Now, this made no sense at all. The only radioactive phenomena known were alpha and beta transitions, which move you one place or two places in the periodic table. You don't go from 92 to 56. That was sort of absurd within the understanding of the time. But that is what they supposedly had found. And that is what, and the amount of energy that's released is vast. And that is traditionally credited as the discovery of nuclear fission. I would query that, and I will tell you why. Because a year before, this is Irene Curie and Frederick, she looking rather sad perhaps because she's missed yet another Nobel Prize, did essentially this experiment, neutrons on uranium, and she identified lanthanum, which is number 57 in the periodic table. I mean, basically the same thing, barium 56, lanthanum 57. So she's discovered lanthanum, can make no sense of it at all, just makes the comment and does nothing with it. So why is it then that a year later, when Hahn and Strassmann do pretty much the same thing and they see barium rather than lanthanum, that they get the credit? The answer is Lisa Meitner. Lisa Meitner has worked with Hahn for 30 years, but she is Jewish. And because of the Nazi pogrom, she has had to flee. And so she has fled Germany earlier that year in 1938. She's now living in Sweden. Her nephew, also a physicist called Otto Frisch, has fled and is working in Copenhagen. And he always visited his aunt at Christmas time. So this particular Christmas, 1938, they meet in Sweden. And Meitner shows Frisch a letter that she has just received from Hahn, in which he says, I have identified barium in these experiments. It makes no sense at all. So Meitner and Frisch, they go off on a walk through the woods on snowshoes, and they stop and have a sort of sandwich and coffee break and say, look, what's going on here? And the first reaction was, from Frisch, well, Hahn must have made a mistake. And Meitner said, no, Hahn is a great chemist. If he says he's seeing barium, he's seeing barium. We have to understand this. And it was then that they had the insight. Now, this is the picture of the atomic nucleus that Niels Bohr had. It's a pretty good one. That the protons and neutrons are very strongly gripped together. Imagine it's like a liquid drop. When a neutron hits it, it will wobble. I'll make it rather dramatic. It will wobble. Let's suppose it distends like this. Now, it doesn't break in two because surface tension will pull it back again. So there's no way they could understand, surface tension would bring the thing back again. And then one of them had the insight, just a second, the difference between a liquid drop of water and a uranium nucleus is the uranium nucleus is electrically charged. So imagine this thing like a dumbbell, like a dog's bone. This end is positively charged, that end is positively charged, like charges repel. Is there enough electrical repulsion there to split it? They did the calculation and found the answer was yes. They found that the amount of energy released in this splitting was vast, even compared with the energy of radioactivity. And this was the moment in my mind when nuclear fission was truly discovered. It was discovered by Frisch and Meitner on a tree stump in Sweden. Not by Hans Strassmann, nor by Irene Curie. They had seen the phenomenon and hadn't understood it. The double irony being that had Meitner not been forced to leave Germany because of her Jewish background, she would have still been working with Hahn at the end of their 30 years of experiments and been there. Of course, it's possible that she might never have had this conversation with Frisch then, so you don't know. But anyway, that's what happened. It is very ironic as well, in 1945, that Hahn got the Nobel Prize for Chemistry for the discovery of fission. Lisa Meitner never won a Nobel Prize. The picture on the right shows many years later Frisch and Meitner being awarded the Fermi Prize by Glenn Seaborg, who was actually the man who discovered plutonium. But I say that a Nobel Prize can be awarded to at most 3 people. The possibilities, it could have been to Hahn and Meitner, because they'd worked together for 30 years and this was just the final bit. It could have been to Frisch and Meitner for having done the interpretation on their own. It could have been to Frisch and Meitner and Hahn. But however you cut it, Meitner would have been in there. But for whatever reason, she was overlooked. So moving towards the conclusions of all this, and making touch now with what became of nuclear fission as it leads to the atom bomb, does this picture show the father of the atomic bomb? Isn't it wonderful? You can't see Einstein's face, but you know that it's Einstein. It's remarkable like that. And that's Robert Oppenheimer talking to him. Now, in the Oppenheimer movie, you get the impression that the moment that nuclear fission was discovered and announced, splitting uranium, that Oppenheimer had a diagram of an atomic bomb on his blackboard in his Berkeley office. I mean, he may well have done. What the movie doesn't tell you is that it just don't work like that. It doesn't tell you that Niels Bohr made the very key observation, which is this. If it's so easy to split uranium and make an explosion, why is it that the rocks of the Earth, which are full of uranium, aren't exploding all the time as they're being hit by cosmic rays? And he gave the explanation. There are 2 isotopes of uranium. They've both got 92 protons, but they have different numbers of neutrons. The total number of protons and neutrons in one is 238. We call it U-238, and the other one, 235. And Bohr, who was really the father of nuclear physics, understood that odd numbers are less stable than even numbers. That it's the uranium-235 which is where the fission liberates the energy. The catch is that in natural uranium, uranium-235 is only 7 atoms in every 1,000. So to get an explosion which requires a chain reaction, you require the incoming neutron to find that 1 in 140. That 1 in 140, split it, and the 2 neutrons that come off have then both of them got to find 1 in 140. The chances of that happening is exceedingly small. The uranium-238 dominates and just blank hits it out. So that is why natural uranium doesn't create a bomb, even with fission, and that is why, if indeed Oppenheimer kept that diagram on his blackboard, he should have done a bit more thinking. I don't suppose he did, but the movie doesn't tell you that. Okay. This is, in my opinion, the father of the atomic bomb. Rudolf Piles, who was a Jewish emigre working in Birmingham, along with Otto Frisch, the same Otto Frisch that we just met, who by then had also moved to Birmingham, they took Bohr's insight, if you like, and turned it around to say, if somehow you could make a lump of 235, how much would you need to make an explosion? And their shock was to discover that you only needed about a kilogram, about the size of a grapefruit, to have an explosion equivalent to 1,000 tons of dynamite, which would emit radiation, which itself would be a hazard, that the blast from it would be so powerful that there'd be no material capable of resisting it. And the immediate panic was, the moment, when you're doing research and you're trying to solve problems or whatever you do, crosswords or anything else like that, you hit your head against the wall. But the moment you see the answer, it's so obvious. Why didn't I think of it already? These guys, likewise, immediately thought, have German scientists already realized this themselves? And that was the moment when the panic set in, that we have now come up with an idea that in principle could change the nature of warfare, and as we now know, that is not an overstatement. The possibility that Hitler's scientists had already discovered that was the reason why the goal was to create such a thing before the enemy could do so. And that is when the beginnings, what became the Manhattan Project, started. It started in Britain, and ways of enriching uranium-235 were investigated by Piles and his assistant, Klaus Fuchs, who is also known as a spy, but that is another story. And by 1941, this all began when the Battle of Britain was still raging. The possibility that Britain was about to be defeated overnight was right there when this amazing discovery of a way that could win the war with this new device that was realized. 1941, the two things became clear. One was that we would be unable to develop the technology for this in Britain because it would be such a huge enterprise, and we were still being bombed by the Luftwaffe. The possibility that the project itself would be destroyed was one reason why we wanted to have it moved across safely to North America. And Churchill also very much wanted the Americans to come into the war. And as part of that effort, he sent a group of scientists across to America with a dowry of the things that we had discovered, like the secrets of radar and various other things were all given to the Americans, along with this insight about how to make an atomic bomb, which the Americans, we now know, had completely failed to realize. We also know that the Japanese and Italians likewise never realized this. Two guys in the Soviet Union independently had this insight, which was classified secret immediately. And I'm sure that the fact that the Soviets knew that this was a possibility was one of the reasons why the spies passing information from Los Alamos was so credible, because they were saying something that the Soviets already were aware of. So there's quite a different story to the reality of the Manhattan Project than the one that you get from Oppenheimer. And if J.D. Vance is listening, I hope you made a note of that. By 1949, the Soviet Union have made their own atomic bomb, thanks to the spies. And by 1955, much more. The hydrogen bomb, thermonuclear weapons. I'm not going to talk about those here for several reasons, but other than to say that if you think atomic bombs are nasty, hydrogen bombs are a completely order of magnitude or more worse. The technical reasons for that, if you want to know, I can say afterwards. But I just thought I would move towards the end with some photographs to set a scene for the punchline. This picture here in the book, is this two guys doing a crossword in the park. Who are they? Well, actually, the guy on the right, Igor Kurchatov, he was the father of the Soviet atomic bomb that was first exploded in 1949. And I love this. I say he's the only person I've ever seen a photograph of who carries his table napkin around growing from his chin. It's a wonderful image. So that is Kurchatov, the father of the Soviet atomic bomb. The guy on the left in later life is there. That's Andrei Sakharov and Vitaly Ginzburg, who were the fathers of the Soviet hydrogen bomb. Sakharov, at the age when he was actually doing the hydrogen bomb development, is shown there. And on the right is the American analog, Edward Teller, who was probably an inspiration for Dr. Strangelove, but that's another story. So it was 1961 indeed, as my grandson said, when Tsar Bomba was exploded. Khrushchev was wanting to make a demonstration. He thought that Kennedy, the new president, was weak, and he wanted a 100 megaton device, which, this is nonsense. You're making things that themselves weigh tons. They're not things that you can drop in an airplane. They're just demonstrations. And Sakharov realized that a 100 megaton explosion would create so much fallout that it would spread around the world and not just contaminate everything now, but enter the food chain and probably change DNA through the generations, that one was really playing with hazards. So Sakharov cleverly managed to cut the strength in two, so that 50 megatons, ghastly though that is, was only a half of what Khrushchev wanted. I think I've said enough. Let's just move to the end to bring things to a state of, well, you hear the words kilotons and megatons. It's very hard to sort of get a picture of what these things really are. So we have the original test of the atomic bomb, 16th of July, next week, the 80th anniversary, the Trinity test. And that bomb made of plutonium was the form that was dropped over Nagasaki and turned out to be 20 kilotons. The uranium weapon dropped over Hiroshima was 15 kilotons. I've added the 15 and 20 together, and there's an almost invisible little thing along the bottom, which is 35 individual little bomblets to represent the combined strength of Hiroshima and Nagasaki. And just to show you the horror of this, this is the nearest I could get to doing so. This is a picture on the ground after the bomb had dropped on Hiroshima, and it was described as like a graveyard with not a tombstone standing. And if you could hold that picture in your mind and imagine that applying everywhere on this aerial view of before and after, that is the effect of exploding the atomic bombs, and that's what that little thing across the bottom represents. So hold that little thing across the bottom, and now this is what Tsar Bomba is. And you begin to realize this is getting utterly nonsensical. And finally, Edward Teller even designed something where each of those represents Tsar Bomba, and it is truly mad. Mutually assured destruction is got beyond it. This was a weapon that could literally, it was called the backyard weapon because there was no need to move it from the construction site if it could destroy everything. We've got to the stage of total immorality, so I will end here with the hero of this story. Who are they and why is he a hero? This is Joe Rotblat. I don't know if any people here have heard of Joe Rotblat. Okay, then I think we all should have. Joe Rotblat is the only scientist that we are aware of that quit the Manhattan Project when its goal was no longer relevant. Remember, the goal was to build an atomic bomb before the Germans did. Now, VE Day was back in May, right? And we have yet to test, let alone to drop the bomb, on Japan. Joe Rotblat was a Pole. He was working in Poland in 1938. He'd just got married, and he wanted to work on nuclear physics, and he'd come across Liverpool University to work on their cyclotron. He didn't have enough money to bring his new wife with him, but he impressed Liverpool so much that they doubled his scholarship. And so, at the end of August 1939, he went to Warsaw to bring his new wife back with him. She unfortunately had had appendicitis and was recovering, so she would be able to come only in another 7 to 10 days. So Joe returned to Britain and Liverpool. Of course, the next day was when the Nazis invaded Poland, and he never saw his wife again, because she ended up as one of the many millions in the Holocaust. The result of this was that Rotblat became, on the one hand, a devout pacifist, and he had an intense hatred of the Nazis. He became one of the British delegation in the Manhattan Project. And that is the reason why, when it was clear that Nazi Germany had now been defeated, that for Rotblat there was no longer any moral reason to be continuing with this effort. He returned to Britain, and he became Professor of Nuclear Physics at Barts Hospital, and he developed many of the things that we now take for granted about the standards of how to use nuclear radiation for good things in medicine, what's the amounts of radiation that you can receive in body tissue before it gets damaged, and so on and so forth. He won the Nobel Peace Prize in 1992. He founded Pugwash, which was the atomic scientists against nuclear weapons. And at the very end of my book, I have a little 3-line pen portraits of all the characters you met, and Rotblat is the final one, and the final line is, he lived to 94, he never remarried. So that is my story for now. Thank you.